Sri Gurubhyo Namma children, welcome to online session. Already we are dealing about coordination compounds. Today I am going to start with oxidation number or oxidation state. We are going to see the definition for oxidation state or oxidation number, and we are going to calculate the oxidation number of central metal ion in the complex compounds. To start with, I am going to define the oxidation state or oxidation number. It is nothing but the charge carried by the central metal ion if all the ligands are removed along with the electron pairs that are shared with the central metal atom or ion. So the definition is, it is the charge carried by the central metal ion if all the ligands are removed along with the electron pairs that is shared with the central metal atom or ion. And now we are going to talk about the calculation. We are going to see how the oxidation state or oxidation number of a central metal ion is calculated. To start with, I have given the complex hexamine cobalt 3 ion. Hexamine cobalt 3 ion. So the complex I have written as in the square bracket CO accompanied by 6 ammonia molecules. Above the square bracket it has got 3 positive charges. So it is a cationic complex because the charge of the complex ion is positive here. So it is a cationic complex. Now we are going to calculate the oxidation number or oxidation state of a central metal ion here, which is cobalt. As it is unknown, I am giving it as X. So X plus 6 ammonia molecules are joined there. So 6 into NH3, which is equal to the charge of the complex. Here the charge of the complex is plus 3. Therefore X plus 6 into 0, ammonia is a neutral molecule, so charge is 0. So X plus 6 into 0 is equal to plus 3. X plus 6 into 0, 0. So X plus 0 is equal to plus 3. Therefore X is equal to plus 3. So the oxidation state or oxidation number of cobalt is plus 3. Now we are going to see another example, that is trisoxalato ferrate ion, ferrate 3. Trisoxalato ferrate 3. So it is a anionic complex because the charge of the complex ion is negative here. So it is an anionic complex. So we are going to see the oxidation state of the ion here. As ion is unknown, so I am giving it as X, assumed as X. So X plus 3 into oxalate ion is equal to minus 3. Oxalate is a negative ligand, so the charge is minus 2. There are 3 oxalate molecules bonded to central metal ion. Therefore, X plus 3 into minus 2, that is equal to the charge, that is minus 3. So X minus 6 is equal to minus 3. Therefore, X is equal to minus 3 plus 6. So you will be getting X is equal to plus 3. So here the charge of the central metal ion, that is equal to plus 3. Next, we are going to see the other important complex here, that is tetrachlorido platinate 2 ion. Tetrachlorido platinate 2 ion. So this is also an anionic complex because the charge of the complex ion is negative here. So it is an anionic complex. Once again, here platinum is an unknown. I don't know the oxidation state. I am assuming it as X. So X plus, there are 4 chlorine atoms. So 4 into chlorine, that is equal to the charge of the complex, that is equal to minus 2. So X plus 4 into chlorine has got a single negative charge. So 4 into minus 1 is equal to minus 2. X minus 4 is equal to minus 2. Therefore X is equal to minus 2 plus 4. X is equal to plus 2. So here X refers to platinum. So the oxidation state of platinum is plus 2. The next one, we are going to say another complex, which is a neutral complex. So I have given examples for cationic, anionic. Now we are going to say neutral complex. The very familiar example is nickel tetracarbonyl. So here nickel is bonded with 4 carbon monoxide. See the charge of the complex. There is no charge over the complex ion here. So it is a neutral complex. So here we are going to find out the oxidation state of the central metal ion. The central metal ion here is nickel. So I am taking it as X. So X plus 4 into carbon monoxide, that is equal to charge. Charge here is 0. For carbon monoxide, it is a neutral molecule, therefore charge is equal to 0. So x plus 4 into 0 is equal to 0, x plus 0 is equal to 0, therefore x is equal to 0. So here the coordination number of nickel is 0 here. We are going to see now the Werner's coordination theory. So this Werner's played a greater role in coordination chemistry. He was awarded Nobel Prize for his coordination chemistry. So his full name was Alfred Werner. We are going to see his postulates. First one, in coordination complex, metal exhibits two types of valencies. So in a coordination complex, metals exhibit two types of valencies or linkages, that are primary and secondary valencies. So in a coordination compounds, metal exhibit two types of valencies or linkages, primary and secondary valencies or primary and secondary linkages. Second point, the primary valencies are normally ionizable. So the primary valencies are normally ionizable. It can be dissociated into ions and are satisfied by negative ions. So primary valencies are always ionizable and are satisfied by negative ions. So it corresponds to the oxidation state of the central metal ion. The primary valencies are ionizable and are satisfied by negative ions. It corresponds to the oxidation state of the central metal ion. The next point, the secondary valencies are non-ionizable and are satisfied by neutral molecules. The secondary valencies are non-ionizable and are satisfied by neutral molecules. And these secondary valencies correspond to the coordination number. The primary valency correspond to the oxidation state, the secondary valency correspond to the coordination number. For example, hexamine cobalt 3 chloride. The name of this complex is hexamine cobalt 3 chloride. So here when you talk about the primary and secondary valency, so Cl, it is a ionizable species, so we can call that is a primary valency, whereas amine, which is a non-ionizable species, so we can call it as secondary valency. Already I have discussed 3 points of Werner's theory. Now we are going to see the fourth point. Secondary valencies are directed towards the fixed position in space around the central metal ion. The secondary valencies are directed towards the fixed position in space towards around the central metal ion. This leads to definite geometry of the complex. As the secondary valencies are directed towards the fixed position in space around the central metal ion, so the complex will have a definite geometry or definite shape. So in modern formulations, such spatial arrangements are called coordination polyhedra. So in modern formulations, such coordination arrangements are called coordination polyhedra. The next point, secondary valencies are shown by thick lines. So we have to differentiate between primary and secondary valencies. Secondary valencies are shown by thick lines and primary valencies are shown by dotted lines. For example, I have written a complex hexamine cobalt 3 chloride. So here cobalt is the central metal ion. So cobalt is the central metal ion. The primary valencies are indicated by dotted lines. There are 3 primary valencies which are indicated by chlorine. So they are indicated by dotted lines. There are 6 ammonia molecules which are neutral molecules which refer to secondary valencies. So they are indicated by thick lines. So NH3 secondary valency are represented by thick lines and Cl primary valencies and they are represented by dotted lines. So this is the explanation for Werner's coordination theory.